And I had one other a couple announcements here before we get started. So good afternoon. Welcome to the CySER webinar. We were excited to have our sponsors that were here last week, and we have some stickers as well as some water bottles for participants that will be coming in from our CySER award sponsors. So we will let people know when those come in so people have access to those. So stickers are always a good thing, as well as water bottles. But today we have a speaker, Slater Weinstock is a security engineer for Casaba Security and a background in working in multiple high-profile projects with clients, including Microsoft and Meta. He focuses on new identity providers, authentication mechanisms, state machines, and mobile app security. He has a Bachelor's of Science degree in computer science from Washington State University, go Cougs. And he's going to talk today about how passwordless authentication works. So Slater, I'll turn it over to you. And I'll just remind everybody to feel free to put your questions in the chat, and we'll go from there.
Awesome. And I'm just popping open the chat really quickly. So if you do have a question and don't feel like asking, you can totally shoot it and I'll try to answer it. As was said, I'm going to be covering WebAuthn, how passwordless authentication works. So this talk's kind of, I don't want to say confusing, but it's a bit confusing just because Passkeys and WebAuthn are very tightly coupled. And there's a lot of vocabulary and there's a lot of steps, and I'm going to abstract a lot of those steps. So just from my end, that's I guess the reason I say that is if it does seem really complicated, it's very complicated. So don't get too hung up on the vocab or anything like that. So WebAuthn, what it really is it's known as the Web Authentication API, and it was created by W3C, so the World Wide Web Consortium, and FIDO, so Fast Identity Online, and it had a bunch of input from a lot of other companies like Mozilla, Firefox, and Google, but ultimately it is just a specification. And what the goal of this is it allows integration into authentication mechanisms that are on our devices, right? And that effectively bypasses the need for a password. So instead of a password, what this is going to be relying on is a public-private key pair. And the public-private key pair in this case is going to be acting as the credential. So in this case, the private key is going to be stored on the user's device. So in the case of me, my iPhone, while the public key is going to be stored on the server. Additionally, there's also going to be a credential ID that is stored on the server, and that's just going to mark what credential it is. That way, when you come to a website, it can find it easily. So some of us are probably really familiar with public-private key cryptography. Some of us may not be. It's also known as asymmetric encryption. I'm just going to go super briefly over it. So as can be implied by the name, public key cryptography or public-private key cryptography, it relies on a public-private key pair. And the data that is encrypted with the public key can only be decrypted with the corresponding private key and vice versa. So really what this relies on is very long numbers, which have a mathematical relationship, which are too complicated to solve without extremely intensive computing power. Bringing quantum computing or something like that gets a lot easier. But ultimately, that is what it relies on. So the common public key crypto example is you have Alice, you have Bob. Alice is sending a message to Bob. What does Alice use to encrypt that message? Uses Bob's public key because Alice knows what Bob's public key is. Everyone else may know what Bob's public key is. It doesn't matter because you can't decrypt it with the public key. You can only decrypt it with the corresponding private key. So Bob is the only one that can decrypt that message because Bob has Bob's private key, hopefully. Otherwise, that's another issue. So let's take a look at just kind of how traditional password-based authentication works. So the common flow is going to be you create a password, the password is going to be hashed, it's going to be salted, it's going to be sent up to the server. And if that same value is ever encountered again in the future, well, you're authenticating to the system. Now, seems pretty secure, honestly. I mean, you have a hash, hashes are supposed to be one way. You're salting it, that's going to increase the entropy significantly, but it doesn't make the password entirely uncrackable. It's still breakable through brute force. If I have my password as password and I press enter, it's going to result in the same value. And additionally, within cryptography, there are a lot of algorithms, there are a lot of methods, there are a lot of order of operations. And it's really easy for developers to make small mistakes which break that cryptographic protocol that they're using, or just use the wrong algorithm. So this isn't exactly beautifully secure, I guess I would say. So the problem here lies in the server is responsible for storing this password derivation or this password information. I, as an attacker, that makes that server a target for me. Now, if you know, assuming you have really high entropy passwords, you're using a credential management system like 1Password or LastPass, you have 28 characters, okay, it's going to take me a long time to break it. I mean, it's going to take out my lifetime to break it. But 81% of all hacking related breaches use either credential leaks or just weak passwords. And weak passwords, 4 digits, 5 digits, 6 digits, 6 characters, 8 characters. It's super prevalent. So not only do you have the server being a target, but you do have that password reuse problem. You have weak passwords, you have those credential leaks I was mentioning, and you have phishing as well. And so phishing, for example, in the case of an open redirection phishing attack, I just redirect someone to a different website, they log in, and I'm like, hey, cool, thanks, I got your credentials. So how does WebAuthn address this? So the server, and I mentioned this previously, it only holds the public keys. Well, public keys are public. So if I'm attacking it, I'm already getting information that I can get anyway. So it makes it not relevant to me anymore. It completely removes that attack vector. So that's a really good thing. Additionally, it also prevents me from entering in a password directly. That helps to mitigate things like phishing. So there are other phishing vectors out there. There are other ways that you may be thinking, okay, so you're not entering a password, I can probably get other ways. And WebAuthn has mechanisms in place to address those and prevent those as well. But ideally, that's kind of what we're doing with WebAuthn. So are there any questions or anything before we get into way more of the nitty-gritty stuff? Okay. So WebAuthn is not as complicated as OAuth, but it's fairly intense. And as can be seen here, this diagram is taken from the W3C page on WebAuthn, but it's ultimately 6 steps. So going through this, we're going to have some terminology. The relying party really is just the application that's performing the authentication of the user, while the browser is traditionally the WebAuthn client, and the authenticator is the device that's actually creating and storing the credentials. And so in the case, so for example, my iPhone, in the case of like a YubiKey, for example, if you have a YubiKey 5 or used a YubiKey 5, it's FIDO2 compliant. It has the ability to actually store the credentials on it. So that's kind of how this is set up. So this is going to get very verbiage heavy. So I do apologize for this ahead of time. If you want me to stop or anything, please just let me know. So what's going to happen is the client is initially going to start by initiating a request to register an authenticator, and it's registering it on behalf of the user. So what's going to happen is the relying party server, the RP here, is going to create an instance of the public key credential creation options. And this is all from the W3C documentation. So that name is just WebAuthn stuff. It's WebAuthn APIs. But it's going to return that to the WebAuthn client, and the WebAuthn client is going to be the browser in this case. So what this will actually include is the user information on the relying party, and what type of credential is being desired. In addition, a challenge is also going to be included, so you can see that there. Now, the challenge really is just a number that's so large, so random, that it probably never existed in the history of the universe up until this point, which means if we ever encounter it again, it likely came after the point in time where I created. So now what's going to happen is we're going into step 2. So we're going from the client, the WebAuthn client, and we're going to start going into communicating rather with the authenticator. Now we're going to talk about that protocol a little bit later. That's called CTAP, client to authenticator protocol. It's a whole other can of worms. But really, the client's just going to call the navigator.credentials.create method. And then the browser is going to do validation that the relying party, validation of the relying party ID against the origin, and verify that that matches. Additionally, it's going to do some hashing of the client data, and it's going to pass that on to the authenticator. So now we're at the authenticator stage, and it's going to pop up and say, hey, yep. Are you good? Do you want to do this? And I'm going to say yes. So the authenticator is then going to create that public-private key pair, and it's going to store that private key. So the private key is now stored. The public key is then going to become a part of the attestation, and then the authenticator is going to sign that with the attestation private key. Now, you can also do cert chain validation if you want to include that. That can happen. Let's not really worry about that. But ultimately, what that would mean is you want to validate that from a root of trust. So you can go fully down the certificate chain and fully validate everything about it, making sure it's a valid certificate authority and all of that. But we don't need to worry about that. So what's going to happen, now we're at step 4, is the public key, the credential ID, and all the other attestation data is going to be passed back into the browser. And that's going to become the attestation object, which is up by 5. Now, finally, that data is going to be returned to the relying party, and the client data JSON object is going to contain the challenge sent by the RP, the origin of the domain that was observed from the client, and what operation was performed. So it's a whole bunch of context metadata. And finally, the relying party is then going to do a bunch of checks to ensure that no tampering occurred during this whole registration ceremony. I should say ceremonies are what flows are called. So technically it's just the WebAuthn registration flow. It's just referred to as a ceremony. So that's going to include verification of the signature over the client data hash. It's going to validate the attestation. It's going to validate the cert chain if that was included. It's going to check that the credential ID is not registered to anyone else. If it is, it's automatically going to fail. And it's also going to validate that the challenge has not changed throughout the entire flow. So that is how you initiate registration with a WebAuthn client. Very complicated series of steps. And I'm going to kind of, I wish I could actually show the example, but then I have to share my screen stuff. Maybe I will, but that is just registration. Then we're going to go into the authentication ceremony. So here's where we're actually authenticating. We've already registered the device. So as you can see, it's pretty much identical. There are some differences. Specifically, the instance is now the public key credential request options. In one, only a challenge is included. That challenge is just used to verify that there's no replay attack factor that's being occurred, that it's mitigating replaying attacks. But it's going to be roughly the same series of steps, just with slightly different API calls. Ultimately, at the authenticator stage, it's going to find a credential which matches the relying party ID, and it's going to prompt the user to authenticate. And then it's going to create a new assertion. It's going to go back through that, and then it's going to return all of that data back to the browser. The browser is going to ultimately finish its promise. It's going to resolve the public key credential, and the server then is going to perform verification, verifying that the authenticator signature actually is using, or it's going to verify the authenticator signature by using the public key that was stored during the initial registration flow. It's going to verify that the challenge created in step 1 actually matches all the way through. That's in the client data JSON object. And it's going to verify the RPID is actually what is expected. The public key is one-time use, right? Technically, no. The challenge is one-time use. It's a bomb oracle. It's dead. The public key here is what's ultimately always going to be stored. Now, if I was doing a brand new flow, then it's going to be a different credential. Does that make sense? Okay, cool, awesome. And if I'm ever like, sometimes I'm completely tuned out of the chat, so just ping me a bunch or say check or something, and I'll totally do that. So, apologize for all of that terminology. So there's kind of something interesting going on here. So there's a potential attack vector here, maybe. So, and this is kind of like a phishing-esque type thing. So let's say there's attacker.com, there's example.com, and the attacker knows the idea of a key ID for a key for example.com. Could you request that signature with the key from example.com over the attacker.com domain? So this is where WebAuthn has a few tricks up its sleeve. So ultimately, the RPID is nothing more than the domain name. So you have an RPID for attacker.com, you have an RPID for example.com. You can't, you could claim any number of subdomains that you want of attacker.com, you can claim any number of subdomains you want of example.com, assuming you're the owner of example.com, or whether the site is coming from example.com. But you don't get access. So if I'm coming from attacker.com, I don't get access to example.com. I can't claim anything about that. So the browser is actually going to put that into that JSON object. And additionally, what's going to happen is the browser is going to put in the origin. So since the attacker.com can claim RPIDs for attacker.com, you can generate real security keys for anything with attacker.com, but you're not coming from the exact same origin. So the origin would be example.com. Since I'm not coming from example.com, it will automatically fail. So what this really boils down to is the security key allowed to do this? And if it is allowed to do it, what origin was used? And then the server does validation of that origin and make sure it's the expected origin. So in this case, because you have those two different domains, they're going to have two different RPIDs. They're not going to match. It's automatically going to fail. It's dead. So that is kind of how it mitigates this. So here's where I say I would do this example. It's really rather boring, but ultimately what happens is you can see that you go to this website, it pops up and says, hey, scan with a QR code. You click that, it pops up a QR code. I would scan that with my phone. So that's kind of what we're doing in essence, and bypassing the need for passwords entirely. Now, the communication between this is where it gets interesting, but also fairly complicated. And so we're going to start to look at the transport of how this stuff's shared. So ultimately, this is what's going on through this flow. We have the relying party, WebAuthn is communicating to the client browser, and now we have this distinction between U2F or CTAP1 as it's now called, or CTAP2. And that's where the client is communicating to the authenticator. So CTAP just means client to authenticator protocol. So this is where things get also fairly messy. So in the case of U2F or CTAP1, you're primarily using this for a second factor form of authentication. The protocol for U2F is pretty easy to understand. The security key doesn't need to know any state. It doesn't need to hold any state. It doesn't need to hold state in memory. The computer just routinely pulls the security key for everything that it needs. And how it avoided that need to maintain state is that when it generated a credential, it encrypted the seed for that private key and gave it to the computer, which acts as the ID of the credential. So the storage was ultimately handled by the server. It was not handled by the authenticator. Now in CTAP 2, it's way more complicated. It's way more involved. There's a bunch of messages that are exchanged back and forth. The security key has to keep state. And ultimately, this is when resident keys started to come in. So because the keys are actually stored in CTAP2 via CTAP2 on the authenticator, they were termed resident keys. That was ultimately confusing. So they became known as discoverable credentials. And a discoverable credential is exactly what it sounds like. It is a credential which is discoverable. So ultimately, you ask the authenticator, hey, I'm on website X. What do you have for website X? And it comes back with, yep, here you go. That's what happens. You don't really need a specific ID or anything. All CTAP is it's a way for the client to speak to the authenticator, and it occurs over NFC, USB, or BLE. So this is where we kind of get into this distinction between Passkeys and WebAuthn. So in WebAuthn, the authenticators are a completely abstract concept. The browser starts CTAP to the security key, and the browser, in essence, does it all by itself on its computer. So if you've used Touch ID on a Mac, for example, so I have Touch ID. If you use Windows Hello or anything like that, that's what's really going on. It's not really a security key, but it is, in this context, a WebAuthn authenticator. So that distinction gets it's a very gray area. Now we're going to move into Passkeys, which is where it becomes an actual security key, or rather your phone becomes a security key. So Passkeys are nothing more than just an extension of WebAuthn, and it just replaces all the need for all your YubiKeys or any security keys with just your phone, so that you don't have to buy and keep track of a bunch of YubiKeys. And really, all they are is just WebAuthn credentials that are backed up and synced across your devices. So the only thing that ever really changed in all of this was how the data is transported between the phone and the computer. And this is where we start to get into the more complicated CTAP and what specifically is going on. So, and you guys have probably seen this before. You scan a QR code, that is pretty easy on your phone. So what happens is you scan the QR code, but encoded within the QR code is a compressed P256 secret. That's just NIST P256 elliptic curve digital signature algorithm. Just in case anyone was curious, and a 16-byte secret key. So that public key is going to be used to authenticate the laptop, and then the knowledge of that secret key is going to authenticate the phone to the laptop. So ultimately, the phone is getting two keys, and then it begins talking with the cloud. So the phone goes to the cloud and says, hey, I'm setting up a cloud or a tunnel. I want to set up a tunnel. I want to be able to communicate this. The cloud's like, yeah, cool. Sounds good. That's great. And then the phone is going to start sending an advertisement, which is called a BLE advertisement or a BLE advert. And that is going to contain an identifier for what the cloud server is. Effectively, it is broadcasting, here's how to talk to me. And it's also going to contain a nonce. So the nonce is nothing more than a key, but that key is necessary or that nonce is necessary because in order for my device to receive a BLE advert, I have to be within close proximity of my computer. If I'm not within close proximity, I cannot receive it, which means I can't do anything. So assuming I am within range, the BLE advert or the laptop is going to receive the BLE advert from my phone. It's going to throw everything into a key derivation function, and the laptop's effectively going to find the tunnel server. It's going to connect with it. And then what's going to happen is there's going to be a noise handshake between the phone and the laptop. Really complicated. Totally understand that there's a lot going on. And I'm going to summarize at the very end, and it's probably going to be like, why didn't you just say that the first time? But that's okay. I like all this stuff. So if you aren't familiar with what a noise handshake is, it's nothing more than pretty much it's based off Diffie-Hellman. So they're going to exchange a bunch of public keys. There's going to be a bunch of operations, a lot of math involved. In this context, it's going to be an NK or a KN PSK that's going to occur. And the handshake, so NK or KN is nothing more than what's called a handshake pattern. So it's a pre-message pattern for the initiator, a pre-message pattern for the responder, and a sequence of not massage patterns, but message patterns. The first letter, so N or K, is going to refer to the initiator's static key. The second letter is going to refer to the responder's static key. So NK really just means no static key is for the initiator, and the K in this case means the static key for the responder is known to the initiator. Now, this is just how it happens. A sample of an NK PSK type handshake is here. That's effectively what it looks like. If the arrow is pointing this way, it's the responder communicating. If the arrow is pointing to the left, rather, it's the responder communicating. If it's pointing to the right, then it's the initiator communicating. This is just one example. It's one of the easier examples to understand. There's a ton of derivations of this. This is not what happens in Passkeys, but just to kind of give you a brief overview, effectively S means the local static key pair, E means the ephemeral static key pair, and PSK is just the pre-shared symmetric key. So the responder is going to be initialized with a pre-shared long-term static secret. That's that S. And it's going to be assumed to be pre-authenticated out of band and stuff. The initiator is going to then calculate a new session secret. So that's the arrow going right. And that's going to add the PSK as a part of the message. It's also going to add an ephemeral key share. And that ES means it's going to calculate a Diffie-Hellman shared secret based on the initiator's ephemeral key and the responder's static key. And then the responder is then going to send a new ephemeral key, and it's going to calculate a Diffie-Hellman shared secret based off the initiator's ephemeral key and the responder's ephemeral key. So really all this boils down to, it's a lot of communication, a lot of math going back and forth, and a lot of hashing algorithms in order to establish this secret. The whole end goal of all of this is the laptop just has to prove that it has knowledge of the private key whose public key was in the QR code, and it has to prove the PSK. And it proves the PSK because the PSK is derived by including it in the Bluetooth advertisement. So if you did not get the Bluetooth advert, you cannot derive the PSK. Therefore, this proves that you are in proximity to your device. So this is different than in 2FA, for example, where, I just had this happen when I was in Ireland. My partner was trying to get onto one of my devices, but effectively, I can still authenticate and say, yeah, that's me. This completely removes that. I have to physically be there in order to receive it. And Passkeys also does some other really cool things where you can start to share secrets so that I could share it with my partner, and then my partner could be able to log in. But effectively, this is just proving proximity. So really all this boils down to that whole thing about CTAP. Phones talking to the cloud, laptop talks to the cloud, a tunnel is established between them. That's it. The tunnel is ultimately secure because of the noise protocol. Let's see, how are we doing on time? Okay. So to summarize, Passkeys versus passwords. It pretty much avoids you from it allows you to avoid using a typable string. The passkeys are generated using secure cryptographic algorithms on the device. The storage of the public key on the server in place of passwords makes the server not a target. The passkeys provide a strong claim that devices are in close proximity to each other because of that BLE. So if a QR code sent via phishing email or QR codes on a fake website, it doesn't matter, I can't receive it. The attacker can't receive it, rather. Which, yeah. Additionally, then the process only occurs between the client and the browser. The website never is involved in any of this. It's only the client and the authenticator, or the client browser and the authenticator. That is everything, and I think I'm at 30 minutes. Apologies for all of that terminology. Really complicated. And then I know I can go into careers in cybersecurity, but decompression for a second.
Any questions?
Yeah, I have a question. Hi, Slater. This is James Crabb. When we're talking about the BLE advert, what is the range on that? So, like, if an attacker wanted to try and hijack that, how close would they have to be?
I don't actually know the exact statistics of that. I have to look that up. Since it's using low energy, you'd have to be pretty close. You're not going to be able to be, you know, like at WSU to my home and be able to get my signal. My guess would be a few feet. I'm not exactly sure though.
Like maybe if you're sitting next to them in an airport or like a table.
Yeah, you could.
Or...
Let's see. Yeah, so yeah, I mean, I'm Googling. I'm cheating. I apologize. I'm actually not super familiar with exactly how close you'd have to be. So that's a great question. I will definitely look that up.
Yeah,
I'll probably add to the PowerPoint
Wikipedia
slide
real quick, but I was wondering, like, because normal Bluetooth is, you know, has somewhat of a range. I was wondering maybe relative to that, be like less or more.
Yeah, this website seems promising. Apologies. Way too much data. Yeah, I'm not actually sure. I'll try to look that up and include a reference to it and include the stuff on the PowerPoint slide before I send it over. Let me take notes. BLE advert range. Okay, so I will take notes on that and add that.
All right, thanks.
I'm seeing ranges. So obviously it's a radio wave, so it's going to depend largely on your transmitter and your receiver. In ideal conditions, which means just like opening, I'm seeing like, let's see, something like 77 meters, which is particularly long. But you know, when you have corners and walls and stuff, that diminishes. I wouldn't expect to be able to pick something up more than 12 feet. So I suppose if you got sufficiently close to your attacker, then that would be possible.
Okay, and so that's a great answer. So yeah, I'd agree with that. I just don't know the exact statistics on. And if the attacker were using a VPN in a server that is close to yourself, does that affect it, or no, that actually does not affect it at all, because still you have to be within that range to get the BLE advert, so you can't do anything. The VPN would just be on network level.
You'd have to plant a bug with a BLE interface.
You can you can do some. You could try, but this, I mean, this is pretty hard to break.
Absolutely.
Did that answer your question? Okay, I'm gonna send. There's no more messages. Any other questions?
I do. I've seen some interesting things come out with universal two-factor, and I'm sure WebAuthn is a part of that. And what's interesting about WebAuthn is, as opposed to the paradigm, you can, as opposed to, like OpenSSH now supports FIDO2 U2F keys. So that's actually really nifty, because you can key a server with an ECDSA key you know, with effectively a second factor, right? You know, you need a hardware key. Do you think there's a benefit or a detriment to having a central control of, like, you know, so then it becomes a classic issue of, oh, who centrally controls this mechanism versus, oh, it's, you know, a user who's, aside from the key itself, half the key stored on the host, half the key stored on, you know, the physical key. Which do you think is better?
Oh, I don't know if I have an answer for that one, actually. I don't actually have an answer for that one. That's a tough question right there. It's a really good question, but I don't know. Any other questions? Apologies if I don't know. Yeah, I definitely, like, this is good stuff. I don't have enough knowledge of, like, how OpenSSH is going to integrate with U2F and stuff to fully answer that.
Oh, they already have. It's actually really nifty. That's why I asked. It's like, so, you know, you got this open source, you know, thing that you can tie between strictly a client and a server, but it sounds to me like, OAuthn is something like a third party, right? It's actually it's significant. It sounds like it's significantly more scalable to user base. So particularly web applications as opposed to remote management. But yeah, it's actually really cool. There's tutorials, you know, there's tutorials on the internet that lay out the framework. You could, you know, it's any the only libraries you need are on the client, and on the server it's all taken care of. So, you know, which is really the SSH piece.
Yeah, that's awesome. Yeah, that makes sense. But I'll have to look that up more.
Yeah.
Any other questions? Cool. So for just the careers in cybersecurity portion, I just want to talk about it for just a few minutes. So what are the careers in cybersecurity? You can do, you can be like a cryptographic engineer, you can do security engineering, you can go into consulting, you can be an ethical hacker, you can be a pen tester, you can do software development related to all the libraries associated with cryptography, with all types of new security features. You can be sysadmins, security architects, CISOs, hardware engineers, hardware hackers. You can work in finance, you can work in the security trades, you can do DRM, you can do government type work as well. I know OMB just released their memo revolving around zero trust architecture for the US government. So that's a very long list, but you can pretty much do a lot of different things in the market. Pretty much tech's always going to be a part of our life. It's always being integrated into pretty much products that we use on an everyday basis. Job growth is really huge. I think the job growth based off from Forbes it's estimated to grow by about 33% between 2020 and 2030. That's 4 times faster than the average. And since 2016, cybersecurity has a 0% unemployment rate. As far as salaries and stuff, salaries are quite high within cybersecurity. 6 figures is really easy to obtain, easy to go way beyond that. So especially if you're good at cybersecurity, you'll definitely be able to do very well for yourself and build a very profitable career. So what I do is I'm a security consultant or security engineer. I work with Casaba Security, but I work a lot with a variety of companies. I'm employed by Casaba Security, but I just consult on different projects for different companies based off what technology they're using. And I'll take a look at either source code, the application. I'll write proof of concepts or exploits for that, and provide guidance on how to mitigate and how to fix that. So yeah, it's a little bit about what I do. Any questions about that? Ooh, pros and cons for consulting like you versus working for the company. So pros and cons of consulting. I get to see a lot of different tech stacks. I get to work with a lot of different engineers. I work in a lot of different languages. I work on a lot of different projects. So I don't want to say companies have a habit of pigeonholing people, but you can become very locked into a certain thing that you are doing, and that is what you're going to do. With consulting, you get to work with a lot of different people and you get to see a lot more breadth of technology. Working in consulting also means, though, you have to become an expert at a person's product in a very short amount of time. So versus a person working in a company may have had a year, 2 years, 5 years, 10 years on a project, you have 4 weeks, 6 weeks, and you have to know all the technology and know how to start breaking it. Oftentimes, we go on the same projects the following year as well. So we do have some running familiarity with it each time that we do it. But that it means that we have to ramp up very quickly. So you have to be very adaptable.
Did you have additional slides?
No, not up here. That was just me talking about. And then the reference component is just all the different
Of 2025,
places.
so.
Yeah. But
those are just different places to look. Okay.
Link. Yep. But yeah, so I mean, yeah, cybersecurity, I really like it. It's a really good field. It's a lot of fun. It's challenging. So, yeah, I mean, if you have any questions or anything, my email's there. You can totally shoot me an email. I'm glad to answer it. If you're looking for internships or you're looking for job opportunities or stuff like that, totally happy to speak to you about that. Or if you're like, hey, I want to work with your company and you've looked this up, I'm the one that you'll first interview with. So I apologize for the torture that you may face. If you have any questions on like the interview process or anything, please let me know. Happy to talk about it.
Yes, so thanks, Slater, so much. We really appreciate. Before anybody drops off, we do have a survey that is in the chat, and we encourage you. It's a very short survey, but it helps us on improving our webinar process and also evaluate for our funding agency. So we really appreciate if you all can take 2 or 3 minutes and do that survey or less. But Slater, we really, really appreciate your time and your openness and in digging into a technical challenge and sharing with us, as well as sharing your experiences. And it's even better that you're alum from one of our partner universities. And so we really appreciate you taking that time. And thanks, everybody. Our next talk will be in 2 weeks. So we wish everyone a very happy Thanksgiving, and we'll look forward to seeing you in 2 weeks.
Thank you very much, everyone, for attending. Really appreciate it.
Thank you, Slater.
Okay.
Thank you so much.
I'm going to drop.